Hello everyone, this is Engineer Sol, and today in this video I'm going to discuss to you about balanced three-phase power system. Three-phase electric power, abbreviated as three-phase, is a common type of alternating current used in electricity generation, transmission, and distribution. It is a type of polyphase system employing three wires or four, including an optional neutral return wire, and is most common method used by electrical grids. So here in this figure, you can see here that the power plant generating the power, and to transmit the power into the loads in the customers through this long transmission line. The power transmission here in this figure is by a three-phase system. Okay? Now, let us discuss first how three-phase AC is being generated. So we have here on this figure is a generator, a 6-pole generator. So there is an armature, a rotating armature here at the center, which is this one. So this source here is a DC source supplying current to the winding of armature. So if there is a current on the winding, there will be a magnetic flux. So these are the magnetic flux generated here on this armature. And this armature is coupled with a source of rotation, which is the prime mover. It can be a windmill, it can be from hydro turbine, right? In order to rotate this armature. So as it is rotating here, it will cut the wires, the winding on the stator. We call it stator. Will cut the magnetic flux, right? So from here, this magnetic flux is cut. So on this side, if there is a magnetic flux cutting action, according to Faraday, there will be an induced or generated voltage across this terminal. So let us show this small clip. As you can see, right? They are 120 electrical degrees with each other. These are the phase which is other. And this is the voltage generated, the amplitude of the voltage generated. The generated voltage is equal to, E is equal to kg, is a constant of the generator, representing the construction of the machine, and N is the RPM, revolution per minute, and Vp here is the flux intensity. So the flux intensity, depending on the flux intensity, of course, depending on the winding, the size of the winding, and the input voltage here. Okay, and also, so since the armature is rotating, it is also related to the frequency. The frequency is equal to number of poles multiplied by the revolution per minute, which is N, and divided by 120. In a balanced three-phase voltages, three sinusoidal voltages are of the same amplitude, frequency, but differing by 120 phase difference with one another. So they are 120 degrees with one another, as you can see from this figure. So this phase, red phase, is 120 degrees with respect to yellow, and yellow is 120 degrees with respect to blue, and blue is 120 degrees with respect to the red phase. And there are two possible sequence. It can be ABC phase sequence, or we call it positive sequence, which means that BB lags BA by BB, which we can say here phase 2 is BB. BB, this is BB, lags BA by 120 degrees. ACB, the phase sequence ACB is we call it negative phase sequence, wherein BB leads BA by 120 degrees. But the most common sequence is the positive sequence ABC. Now again, as I've said, this is the generator. This is the armature rotating inside. We'll put it here inside, and once it is rotated, there will be an induced voltage across these terminals, right? Between this, and in this case, it's connected. The other side here is connected together. We can consider that this point here as the neutral, and this is going to the the line, which is this connection. As you can see from here, this is called the Y connected source, right? So the connection of this generator is Y connected, employing the sequence RYB. RYB is the UK standard sequence, or this sequence is positive sequence RYB. Okay, and you can see from this cable, this is a standard 3-phase cable. We have RYB, so red, yellow, blue, and here we have the black. Here is the neutral, and of course here there's a wire here also. This one will represent the ground, right? This will also represent the ground. So this is RYB neutral, and this one here will represent the ground. Now, high voltage AC can be transmitted a long distance without applicable loss and readily transformed to low voltages for practical use, right? As you can see, power plant generation, 13,000 volts. With a transformer, step up to 345. Another transformer to step down to 69,000. And another transformer to step down another to 13,200. Now, question, why do we need to step up the voltage? As you can see, this represents a very long distance, right? This tower, you can see from outside. Maybe you can see from outside there are very long distance. There's a power is being transmitted. Now, whenever there is a current flowing here, of course, when there is a current is flowing here, there are losses. That the P loss actually is equal to I squared R. Okay? So, if the current I is high, we will have a very high voltage. We will have a high power loss. If the current is less, we will have a smaller power loss. Okay? And if you increase the voltage, the current, the current will decrease, right? Because of constant power. Beware, you are transmitting a constant power. If you increase the voltage, the current will decrease. So if we increase the voltage here, the current will decrease, reducing the power loss. Okay? So now here, this is one customer, one type of customer, industrial customer. They have they have their own transformer. They will step down 69,000 up to their utility voltage, right? 69,000. So this is the transformer here. So again here 69,000. Again we have 13,000 volts. So here another commercial, they have their own transformer to step down to 13,200 their utility voltage. And of course here, to our residential, we have here another transformer to put it into 20 volts or 240 volts, right? 13,000 into 220 volts. So there are so many different transformers. If you look at single line diagram, right? 13,200 step up to 345K, and 345 step down to 69 for the secondary transmission, and 69,000 to 13,000, right? So it's again step down, and up to some customers, like 13,200 from here, and then 13,200 to 415, right? To 415 from here, or another one here from customer. I have another transformer from here, 13,200. I can have another transformer here up to the residential, right? Residential, which is 240 volts or 220 volts going here to this residential. Now, in this part, let us say in this part, industrial customer, and here commercial, another building, we implement this low voltage switch gear because there are a lot of circuits here, a lot of loads. So as you can see from this one line diagram, this is the main breaker, this is the main bus bar, and it's distributed to different panel boards. Let's say this is one supplying first floor, second floor, third floor, and so on, right? So we have this bus bar. As you can see here, these are the bus bars. There are three bus bar here. One bus bar for red, yellow and blue. As you can see here at the back, there is bus bar. It's speeding the breaker, air circuit breaker. And then these are the circuit breaker going to the panel boards. These panel boards here can supply different branches also of panel boards going to our, let's say, different in the hotel, room 1, room 2, room 3. There are different panel boards also, and also this. This is what what's going on in the power system. Now, advantages of three-phase, more efficient, because if we transmit three-phase, we are only using 3 wires, right? 3 wires. If we are transmitting single-phase, we are using 2 wires. So we don't need 6 wires to transmit a three-phase. We need only 3 wires. So it's more economical, and the power is multiplied by 3. So we have a good advantage of that. So industrial application, high power motors have constant power torque. So if they are using three-phase system, three-phase motors are self-starting. They have high starting torque using three-phase. Parallel operation is easier. Let's say parallel operation. Then let's say in one power plant there are 3 generators, right? Now, if we have an increase, we have a high load. Let's say we can run 2 generators, generator 1 and generator 2, and to be connected in parallel, like a battery. But there is an equipment called synchroscope. Synchroscope is used to check if the generators are suitable to make it parallel, to operate in parallel. So you need to satisfy the conditions to make it parallel. It must be same voltage amplitude, same frequency, same phase sequence. Then it is the time to connect it to the grid, to the other generator. So high efficiency, right? Because three-phase has a higher frequency. Three-phase motors have uniform torque and also high power factor. So these are the advantages for three-phase. Now, when we are implementing three-phase, in this figure here, you can see how we distribute the power. This one is a three-phase motor. Three-phase motor, of course, it is connected to RYB, and a single-phase load is connected to neutral, and one line red and neutral. And here is connected to yellow and neutral. And this pan is connected to blue and neutral. In the panel board, how do we connect that? This three-phase motor connected to RYB, right? And this one here, the light is connected to yellow and neutral. In this case, this is the neutral. This black here is the neutral. So it's connected to yellow, and this one to be connected to neutral, single phase, right? And here we have red and black. So this one I can connect it to red, and I can connect it to neutral. I will have single phase. What about here? This is connected to blue. I can connect it to blue, and then I can also connect this into neutral. So we will have a balanced load on the panel board, right? And this one here is the ground, okay, for protection. Look at this cable. This is another cable. We have RYB, and we have neutral, and we have a ground, right? Now, three-phase voltages connected to the load can have different configuration. We have Y source, Y connected load, or we have Y source, delta connected load, or we have delta connected load, delta connected source connected to Y connected load, and we have delta connected source, and we have delta connected load. So we have 4 configurations. Now let us now go and analyze Y connection. That means Y source, the source is connected in Y, and the load is connected in Y. So this here, this schematic diagram here, so where is the source? This side here is this is the source side. So this is the generator side, this is the source. So since this is the source, we have the source also is a generator. So as you can see, as I discussed to you, the generator is consisting of winding, right? Different windings. So it has an internal impedance, set S and set S, right? And the power transmission line that I showed you earlier, it has also an impedance. So it can be represented by ZL, right? ZL also here and also, or not here. So this is set line, okay? So here set line and also from here this is set L, okay? So and we have a load. This is the load side here. This is the load side. So this is the load, Y connected load. So it has the impedance of the load, set L. It's a balance. We're talking about balance load. We can set all of them set L. Now, to simplify our analysis, we don't have data, exact data of the impedance of the generator and impedance of the line. We can assume that we can combine all of them as one single load. So we can call them as set Y, right? So simplify our analysis. So let set Y equal to set S, set L of the line and set of the load, right? Okay? So now, notice here on this figure, we will have, let's say this is IA, this one here is IB, or let's say this is I1 is equal to IA, IB equal to I2, IC is equal to I3, right? And we have a voltmeter E1 measuring the voltage across set 1. Remember, we're talking about balance load, right? So balance load means Z is equal to Z1 is equal to Z2 is equal to Z3. All the impedances are the same, right? Now, let us draw the phasor diagram of the voltages. So what is BAN? So E1 is measuring BAN. Let us use BAN as a reference. We can say that BL over square root of 3 angle 0, right? Where did we get that square root of 3? So I'm going to discuss it to you later. BBN here is equal to, they are 120 electrical degrees, BL over square root of 3 with an angle of negative 120 degrees. So this is BBN. BCN here is equal to BL over square root of 3 with an angle of 120 degrees with respect to the reference. What's the reference? BAN. Okay? Now, what about BAB? How did we get the value of BAB, BBC, and BCA? So, what is BAB here? BAB is the voltage between A and between the terminals A and B. So, notice here that BAB is equal to voltage BAN plus BNB, this voltage, right? BNB. So, BAB is equal to BAN plus BNB. But what is BNB? BNB here, this is BBN. BNB is the opposite of BBN. So, where is the phasor? If you plot the phasor of BNB, it will be what? On the other side, right? On the other side. So, this is called BNB, right? BNB. So, meaning to say, BAB is equal to BAN plus BNB will give you, vectorially, if you add this together, you will have this vectorially, we will have the value of BAB. But how did we get the 30 degrees? Let's continue. So, BAB is equal to also a negative of BBN. So, BBN here, the negative of BBN is BNB. So, what is BAB? BAB angle 0. And minus BBN, my angle negative 120. Minus, right? So, if we implement this one, simplifying the calculation, we will arrive in that BAB is equal to square root of 3 BP, right? BAB is equal to square root of 3 BP with an angle of 30 degrees. That's why we have 30 degrees here. So this BAB here is equal to square root of 3 BP. So we have, let's BAB is equal to square root of 3 BAN or BP with an angle of 30 degrees, right? Because I use BP here because BAN has same magnitude as BBN, has same magnitude with BCN. To make it simple, let's say this is voltage BP, right? Okay, now let's have, what about BBC? BBC here, as you can see, is equivalent to BBN plus BNC. So BBN plus BNC. So what is BNC? This is BCN. BCN here. But BNC is on this other side. If we add these two phasor together, we will have our BBC, right? You know, this is a vector addition. So we will have BBC is equal to BP angle minus 120 minus BP angle 120, right? Minus BP angle 120. So we will have BBC angle negative 90, right? BBC is equal to BL angle negative 90. So it will be on this part, this spacer here, right? We already have this spacer. What about BCA? BCA, as you can see from here, is equal to BCN plus BNA, right? BCN plus BNA. So this is BNA. So it will be BAN here. BNA is on the side, so right? And if you add these two phasor, vectorially you will have BCA, the same with our analysis before. We will have BCA angle 150, right? Now, as you can see, we have this is the phase voltage, this is the line voltage as I've written here. We have B line is equal to square root of 3 B phase in terms of magnitude, right? B line is equal to square root of 3 B phase in terms of magnitude. Okay, so what is BP here? From here, that means BP is equal to B line over square root of 3, right? Okay, so it means here, that's why we have here B line over square root of 3. B line over square root of 3, B line over square root of 3. Now, of course, when we analyze the load and the source, we have to analyze also the power consumption. So let us use a wattmeter. Wattmeter is consisting of a current coil and a voltage coil, right? So current coil and voltage coil. The current coil is in series with the load and the voltage coil is in parallel with the load. In our connection earlier, you have I1, E1. It is measuring what? It is measuring the power. We can say this is wattmeter number 1. We can also say that this one here is wattmeter number 2. We can also say that this one here is wattmeter number 3, right? And the total power is the summation of P1, P2, P3, or the reading in wattmeter 1, wattmeter 2, wattmeter 3. But remember, we are talking about balanced three-phase system. Balanced three-phase system. So we are talking about balanced three-phase system. All W1, W2, W3 are equal. So just multiply it by 3, we will have the total power. So in terms of equation, P total is equal to 3. What is the power for this single impedance? What's the power here? BAN, IAN, right? The IAN is the current flowing here. Cosine of the phase angle of theta B minus theta I, right? So this is the power for each, right? This is the individual power. Multiplied by 3, we will have we have to simplify the equation. What is BP? BP is BL over square root of 3. Cancel this 3. So this 3 will become, because 3 is equal to square root of 3 times square root of 3, right? So cancel the square root of 3. We will have square root of 3 here. And we will have BLIL, cosine of the phase angle between the current and the voltage. So this is the general equation to calculate the power consumed in a three-phase power system. Okay, so let's go back again here. We have I1, E1 to measure the power W1, W2, W3, right? So to calculate W3 in terms of mathematical calculation, W3 is BCN, ICN, cosine theta B minus theta I. So let us have an example. Let's example that our impedance is equal to the purely resistive load. So, if it is a purely resistive load, that means this theta B minus theta I will become 0, right? This is 0, cosine 0, it will becomes 1, right? This part here is 1. So, how you calculate, let's say, omega 1, W1 is equal to BAN, IAN, right? Multiplied by 1, right? So, now omega 2, W2 is equal to BBN, IBN, cosine, they are in phase, so cosine, so we will also have 1. So omega 3 will be B, CN, I, CN multiplied by the phase angle between them, which is also 1, right? Cosine of that angle. So we'll have the total power. Now, let's say we want to measure a line-to-line voltage. We have current. We are measuring the current. This current flowing here is the same current that flowing here. I1 is equal to IA is equal to IAN, right? These are the current that flowing here. The same current. We are talking about the same current. But now the voltage, I am measuring the voltage between A and B. This is called B line, right? So, this I1 and and E1, it will, if we, in our system, in our lab volt system, in our wattmeter, it will multiply immediately. It can automatically, in using wattmeter, it can automatically calculate the power. But this power is not the correct power. So this will have a value, of course, W1, W2, W3. But since you are measuring line-to-line voltage, this is actually a wrong power. So this is not the way to measure the power of a three-phase power system. It should be voltage across the impedance and the current passing through the impedance to the same impedance, right? So it will be the current passing to the impedance and the voltage across the impedance will give you the correct power, right? So this one, this connection, you cannot take the power. So this is